But it also doesn't contain extraneous information, like it doesn't contain the lane markings, et cetera, which would be important to drive. If we contrast that with what we give a robot to navigate, it tends to look like something like this. So it's very metrically accurate. This is a map of the same environment from the Kitty dataset, but it contains an awful lot of extraneous information that's not useful for navigation. And it's also incredibly difficult for us to interpret, and not a very useful map in terms of communicating between humans and robots in terms of how to get from place to place. And if we think about higher level autonomy, like I described earlier, imagine asking a robot, and this is a real example taken from a deployment that we did with Army colleagues at West Point. You have a mission that you want the robot to do, which is to go to a particular location. You communicate information about what's in the environment, like the bag is and the trash are both suspicious. And the robot needs to interpret those in terms of securing the area, going inspecting those, and then understanding what is meant by the tree in the road in the presence of many, many trees. And so the question is, how do we actually get at this kind of higher level understanding and shared situation awareness between humans and robots? Now, if you were at the debate last night, or if you've been following the literature for the last 3 or 4 years, there's been an awful lot of discussion around not really needing maps and not really needing representations of the environment, and really relying on generative AI and large language models to essentially bridge that gap. And there seems to be a lot of claims that LLMs can do all of the things, including planning. Why do we even need a kind of hierarchy of representations? Why do we need abstract representations, et cetera? And I'm not going to spend a lot of time on this, and this is a slide that I've shown a couple of times, but really there's actually a continuum of possible approaches to these problems. On one side of the continuum, you have a structured model of the kind that I just showed in terms of a map. And we know how to do things like localizing that environment. We know how to share information about that environment. We know how to generate plans. But we don't actually have good ways of articulating what is the right level of abstraction for the purposes in particular of navigation for a human. What we do know is that these kinds of models are usually interpretable. They provide guarantees in terms of performance. They're also very efficient to learn. Like we know how to build maps as roboticists. We do take a little bit of, or in some cases, a substantial computational hit. On the other hand, we have these learned policies that are certainly more flexible. They're almost certainly more computationally efficient. We don't have to do a lot of extra work in terms of teaching our robots new skills, but they are very data intensive. And so the kind of thing that I'm looking for is a focus on the representation that gives us the best of both worlds. How do we actually extract the right representation for the purposes of not only computationally efficient navigation, but also shared information between humans and robot partners so that they can do things like navigate and also carry out the more complicated mission I showed you earlier. And one claim that I'm going to try and make is that reliable and especially long duration social interaction requires true understanding of the environment. And what it defines true understanding is really a question of what is the right representation for social navigation. So on the representation front, we can actually go back to the late 90s and 2 independent streams of researchers, computer vision and also computational neurobiology, landed on the same idea, which is the world is composed of things and stuff. So things tend to be discrete objects in the world of the kind of thing you can imagine like YOLO extracting and putting a bounding box, or SAM extracting and putting like a nicely delineated segment boundary around the objects. But if you have stuff in the world, that tends to be the things where there isn't a clear notion of a distinct entity that is rigid or articulated, and it's not even clear necessarily where the boundaries are. And so I can put bounding boxes around all the things in the environment, and presumably by calling YOLO. We might argue about whether or not the flag is a distinct thing in the world, but it tends to be like a highly localizable thing. You start to get a little bit fuzzy around the tree. Is the tree and the tree leaves things or stuff? And then when you get to like the actual pavement in the environment, the boundaries, well, okay, so in Manhattan, probably the boundaries of the pavement are pretty distinct. But if you go into like less structured environments, more outdoor environments, and the boundaries of the drivable surface, the walkable surface get very fuzzy indeed. And what's really interesting to me is that the things are very easy for us to train a object detector in order to like identify the environment and use as landmarks for navigating our way through the environment. But as a signal for where we should navigate and how we should navigate, the stuff is actually far more useful. The stuff is the trails, the stuff are the paths in the environment. And so a very useful thing that we could do is actually change how we think about the navigation problem as distinct from building, point features in the environment that we're navigating and trying to avoid collisions, but actually extracting a notion of the navigation signals in the environment and using those to find our way through. So this is an example of a flight that this video is due to my former postdoc, Marcus Rill, now faculty at TU Munich, and two other students in my group, Jake Ware and John Carter. And they used a semantic segmentation engine. And this is from a couple of years ago. It appeared last year, but the work was done a couple of years before that, prior to SAM, but where semantic segmentation was really starting to actually work well as a technology. And extracting the road surfaces, the grassy surfaces, the sidewalks, et cetera. And the segments themselves aren't necessarily all that useful, but actually retracting them to a motion graph all of a sudden becomes quite useful. And so this is sort of my first attempt to articulate how we actually represent the world for the purposes of navigation and communication between humans and robots can make a tremendous difference in how well we can navigate outside our more traditional domains of self-driving cars on well-mapped roads and in-service robots operating in factories and warehouses where we have detailed geometric maps, we know the world ahead of time, and we can do our traditional motion planning optimization for navigation. We also need a abstract representation for efficient planning. So in that architecture that I showed with that continuum, only on one end of that continuum did I have an obvious place for a representation of the environment. So one of the things that we have started to do in my group is to start to work with Luca Carloni and his student Aaron Ray. Luca, for those of you who know his work, has been doing tremendously good work in building scene graphs. Luca comes from SLAM heritage of building detailed geometric representations of the environment, but he has started to build hierarchical representations of the environment that take the very low-level geometric mesh that we use for collision avoidance and start to abstract representations of places and rooms in the environment, buildings, objects in the environment, and actually maintaining explicit representations, or explicit linkages between the representations of the different levels of the hierarchy. And what this allows us is all of a sudden to be able to solve very long distance, long duration navigation problems driven by human level instructions and also human level descriptions of the environment, because we can plan and we can ingest information at the higher levels of the representation. We may not even necessarily be able to ground the higher level of the representation in the low level geometry until we enter that environment. So now we have a mechanism for navigating in environments where we don't even have a model of the geometry yet. I'm not going to talk in detail about how this model is represented, but the really nice thing is that the higher levels of the abstract, so the lowest level of geometry, you can basically give to any motion planner. You can give it to OMPL, and it will solve the motion planning problem. But I think we can all agree that for complex navigation problems, we don't plan our way to Hartsfield at the level of the dense geometry. We rely on abstract representations of exactly the kind that Luca and Aaron are giving us to plan at the highest level in terms of I'm going to get an Uber from the Omni. I can plan my way to the Omni. I know that the Uber will take me to the airport, and then I can plan my way to the TSA pre-check, et cetera. I can generate a plan at that level. The upper level representation of the scene graph basically corresponds to the kind of information you get from a human and the kind of information you want to give to the symbolic planner to be able to plan those long duration missions. And then they're connected to the low level geometry when you have it for the specific motion plan. One of the problems, if you go to Luca and say, will you give me a scene graph? And let's leave aside the issue of you may not have seen the entire environment. Let's assume that you've mapped the whole thing. And you say, give me a scene graph. He'll give you a thing that looks like this. And it's incredibly dense. You give the upper level representation, the abstract representation to an abstract planner like PDDL planner, and it's just going to fall over. It's going to say, what the heck is this? It's way too dense. I can't plan at this level. And the reality is just as I argued at the beginning of my talk, where the representations that we get from our SLAM solutions are really poorly aligned for what we need in terms of humans and robots working together, social navigation, or long distance, temporal extended navigation. It contains too much information. The abstraction is poorly aligned with the problem. And so we need some way of actually refining the abstraction for the problem at hand. And, the point here is the number of task skeletons that we need to consider for long plans basically explodes, even at the upper levels of the abstraction. So we need some mechanism for finding sparse abstractions. So working with Luke and a student, we've come up with two possible solutions. One is that you can identify redundant symbols. So for instance, you can take just the simplest version of the problem, such as like navigation, and you can throw away every symbol that isn't implicated in the goal. Throw away every symbol that is implicated in the goal. You're not going to actually be able to solve that planning problem. You can iteratively refine the abstraction, adding back in symbols as you discover you need them until you can actually come up with a representation that is relevant to the problem at hand. The second thing that you can do is you can factor the planning problem into like the navigation piece, in which point you can throw away all of the symbols that are unrelated to any kind of navigation problem, solve that navigation problem, and then put back in the problems that are related to anything else you might need to do. For instance, if you're doing mobile manipulation. So we have a couple of approaches here to coming up with these ways of getting at a navigation relevant representation from the abstracted but still unnecessarily verbose representation given to us by the scene graph. And so this here is a video just of the robot taking an instruction in order to like find its way through an environment. I think in this case, it was given a particular instruction to go to a location. It discovered that the route was obstructed, and so it's able to replan when it discovers the abstraction, move the object out of the way, and continue on. In terms of a social navigation example, this is perhaps a little bit further afield. The video here shows that the actual goal specification was given in this very abstract representation. One of the things we've done in the last couple of months is actually connect the low-level navigation planning here with a natural language interface. So now we can actually give instructions in natural language text and have the robot follow those instructions very nicely. It's almost to the point where the students actually like to just move the robot around through the world by typing natural language instructions to the robot, because the symbol grounding and the motion planning interpretation of the instructions has gotten that reliable, which is also really satisfying. We have some results here that basically show, give some sense of the computational complexity. As we sparsify the environment, then we see that the actual cost of solving the plans goes down. This is a log scale, and so it goes down very nicely. A thing that you might be worrying about is like, well, what happens if you actually start to need all of those symbols? And it is the case that as we grow the complexity, so along the x-axis here is the number of actual PDDL objects that are actually required in order to solve the plan. As the number of symbols is actually required to solve the plan, then the computational actually starts to grow, and we see very little gain in terms of our sparsification. But at the end of the day, these are not the kinds of problems you could solve as just straightforward navigation problems. If you want to get high-level instructions, high-level interaction from a human partner, then you need this kind of symbolic abstraction, and you need some way to actually match the complexity of the representation with the complexity of the planning problem. An important point here, though, is that we are relying on we're relying on the perception system and the SLAM system to give us the base level of symbols that allow us to do that navigation. So I talked early on about using the stuff in the world and semantic segmentation as a retraction for the purposes of navigation. I didn't say much about distinct objects in the world. I didn't say much about the things at that point in time. And that's because things are actually kind of tricky in the world. Geometry is if you actually need the geometry, for instance, if you need to know the position and the size of the objects for the purposes of landmark-based navigation, you get some kind of instruction to meet at the large ICRA sign by the registration desk, then you need to know where that is in the world, and we're relying on the perception system. One of the things to note is that our ability to actually localize objects in the world is often much less good than we would like it to be. It's not a problem with detecting these worlds. Computer vision has given us very, very nice ability to detect these objects in the world. But actually localizing them in the world and using them for navigation, as humans often do, is less reliable. Part of that loss in reliability comes from the fact that these things are partially observable. I can accurately detect that car in the image, but I actually can't accurately get an estimate of where that window is in the world. Why I don't have an accurate estimate? It's partially occluded by this pillar here. So this bounding box isn't actually capturing the full extent of the window. Here, I'm losing the full extent of this window here by virtue of being cut off in the frame. So that partial observability means that only some of my state variables are actually observable at any point in time. We need a way to actually deal with uncertainty. When we're dealing with people, when we're doing social or otherwise, human involved interaction, we actually need to be able to capture our uncertainty. There's a couple of different types of uncertainty in the world. You may have heard these terms before: epistemic and aleatoric uncertainty. These are fancy words for basically aleatoric uncertainty is the fundamental ambiguity or stochasticity in the world. Like, it's a coin flip as to whether or not this is exactly where the window is, or this is even a window. Contrast that with epistemic uncertainty, where there may be an entity in the world that you have no training data for. You have no model of exactly what that is. That happens a lot to us. As we've been investigating these human interaction forms of navigation and mission execution, we regularly encounter objects in the world that we are outside the training support of our training set. They're what are known as out of distribution. And so one of the things that I think is really important is that our representations support notions of uncertainty. We need some way of actually knowing what we know and what we don't know, either so that we don't put it, if it's really unreliable or we don't know what it is, we don't put it in our representation. Or if we're getting a reference from a human partner in terms of an object in the world or a place in the world that we don't recognize, we need some way of querying the human partner for clarification. I'm not going to spend a lot of time on this, but one of the things that we can do is we can recognize like partial observability that is a form of aleatoric uncertainty. You can actually scale your representation. So again, this gets back to the question of representation. Is putting a bounding cuboid around every object that I see in the world the right answer when I can't necessarily observe, or I don't have full rank observability over the position of the object or its extent? This video on the left here shows what happens when I try and localize these. This is simulated data. I'm localizing these objects in the world. If you look carefully, you see the estimates are roughly in the right place in the world, but the actual extents of the bounding cuboids are wrong. And I end up taking paths that are likely to be in collision with those objects because I estimated them incorrectly. If instead I give myself the ability there we go. If I give myself the ability to allow myself to only estimate some of the variables, so I might not estimate the direction or the extent of the bounding cuboids, and I actually put like a more conservative estimate around them as I move through the environment, then I'm actually going to do much better in terms of my navigation strategies. So it's really important that when we build these representations and we use them for navigation, especially when we're doing very low level geometric navigation, but more semantic navigation based on objects in the world, that we actually give ourselves representations that are robust to loss of observability, that are robust to the inherent uncertainty. I have a bunch more slides here related to other forms of uncertainty, but I'm going to skip ahead to just the end here and say that we need, we know we need abstractions to represent the world for the purposes of communicating with humans. The ways of getting at these abstractions are starting to emerge through things like neural network driven computer vision techniques. We have the ability to detect stuff for the purposes of navigating drivable surfaces. We have the ability to detect landmarks and objects in the world for the purposes of accepting missions from humans, for the purposes of using those landmarks in the environment. But those abstractions have to give us robustness. They have to be robust to loss observability. We have to be able to use them for efficient planning in order to get computational efficiency in executing the plans over long length and timescales. So this work, I got to thank all of the students and postdocs and collaborators like Luca and Marcus that I've worked with. Also want to thank the sponsors that have supported this work, and thank you all very much for your time and attention too.